Science and Metallurgy course. I am Chandrasekhar at Nallamala Reddy Engineering College, Hyderabad. In this video, we will be discussing about second chapter, Unit Outcome 2, that is, Define and Explain Binary Phase Diagram and its importance. Let's begin with very important topic in material science, that is phase diagram. So this will constitute a sort of chapter in our material science course. Let's begin with an introduction to the phase diagrams. It is best to introduce with an example. So let us take an example, copper-nickel alloy. Now let us look at some basic points about the copper-nickel. Copper is a cubic closed pack in a crystalline structure and it melts at 1085 degrees Celsius. And nickel is also a cubic closed pack. Its melting point is a higher melting point at 1453 degrees Celsius. So, if we simply look at, let us say, look at copper and this vertical axis to represent temperature in degrees Celsius. And on this temperature axis, we have marked melting temperature. So we know now above this melting point temperature, the phase which will be present will be in the liquid phase, and below the melting point a solid phase, and only at the melting point both phase will be available. Now let us look at nickel, and melting point is higher at 1453 degrees Celsius, and above the melting point we have liquid phase, and below the melting point solid phase, and at the same melting point both solid and liquid equilibrium condition. Now let me say the x-axis is weight percentage, is nothing but composition. So here copper has 100% weight percentage and 0 weight percentage nickel, and here pure nickel itself is 100 weight percentage. So the composition axis varies from 0 to 100, and if you take any point in between, so that will be 50%. So any alloy of copper or nickel will be some point in this axis, maybe 10%, 20%, 50%, 80%, 90%, and so on. So any alloy, which I mean will be some point on this axis. So entire copper nickel system is represented on this x-axis from copper to nickel. And in particular, let me focus on this 50% of alloy. So here in this phase diagram, for 50% of copper and nickel alloy, where only important points melting point temperature, and we know all the phases above the melting point and below the melting point. What are the phases? Now the question is, what will be the critical melting point temperature for 50% of nickel alloy? So it will be somewhere on the line. And not knowing anything about the system. Assume that we don't know about this system. So what we can try to do is do a linear interpolation between these two melting points. In other words, assume that the melting point varies linearly from the melting point of the copper to the nickel, as we are vary the composition. Then obviously 50% of alloy, which is our interest at the moment. So this melting point will be predicted exactly in between the copper and nickel at melting point. So we will get the melting point of the alloy, the predict melting point, that is mean value of melting point, is equal to what? 1453 plus 1083 divided by 2. That is nothing but 1269 degrees Celsius. This is a reasonable prediction that copper is melting at 1085 degrees Celsius and nickel is melting at 1453 degrees Celsius. So at an intermediate temperature, at an average temperature of 1269 degrees Celsius, our alloy is, that is 50% of copper and nickel alloy will melt at this temperature. But when we will do this experiment, actually we will find the liquid start appearing at a temperature lower than what we have predicted. So below 1269 degrees Celsius, the melting actually begins. If we do this for different alloy composition, then we will find, suppose instead of 50%, now we will make 20% of copper when the liquid begins, and similarly where 100% liquid forms, and similarly 80% of nickel. Now if you will do experiment for all different alloy composition, and we will be finding melting point temperature for all different combination of alloys, and these boundaries will call liquidus boundary, and this boundary is called solidus boundaries. Now what we mean is that whatever the range of liquidus and solidus boundary temperature, above liquidus we have a single phase, that is liquid, and below this solidus we have a single phase, that is solid phase. So here solid phase in phase diagram is usually written Greek letter alpha. Since this alpha, you can see this alpha will contain both copper and nickel alloy. So it's a solid solution. So copper and nickel are almost the same size, so they make a substitutional solid solution. So this alpha is a solid. Recall the Hume-Rothery rule that now we are having solid substitutional solution right from one end to the other end. So this fact is related to the Hume-Rothery rules, possible only two solids at the same crystalline structures. And here we have fortunate that both copper and nickel is possible. So this completes our phase diagram, where the x-axis is the composition, which starts from 0% nickel, actually which is a pure copper, to 100% nickel, which is pure nickel, and y-axis is a temperature, which starts from low temperature to high temperature, including the melting points of both the components. And we have two boundaries in the phase diagram. One is liquidus boundary, above which liquid is stable, and a solidus boundary, below solid phase is stable. And length shape is between liquidus and solidus, where both phases are stable. So this is the phase diagram of copper nickel components.